Now that we've seen how a linear-ish function behaves, what can we do if we have a curve, something that doesn't really look like a line anywhere, but we'd like to treat it like a line in some places? So let's go ahead and sketch a curve here. And let's look at a few particular regions. So in this particular box, a very small region of the curve, if we pick a point that we'd like to be near on this curve, we can approximate a line at that point. Likewise here, we can pick a new region of the curve, take a point that we like, and we can draw a line at that point and say that the curve at this point is approximately a line. And here's another region where we have a small part of this curve that looks like a line. So we can pick a point on the line. We'd like to be here on this curve, and we can approximate the curve at this point with a line. So if we get too far away from this point, it doesn't really match our line anymore. But we can now treat the system as a linear-ish system, and now we can try to approximate it by moving the axis to this point. So how do we pick where these points are? This is where I'd like to define something that we're going to call an equilibrium. So in an equilibrium, we're assuming that we have the definition for how the system is behaving. So for a dynamical system, we have some expression for the time rate of change of the state. And so the time rate of change of the state is equal to some f of xu. This is a nonlinear function, perhaps. And so let's assume that there's some x0 and u0 for which x dot is equal to 0. That is, I'm going to pick a point x0 and another point u0. So if I plug them into the function f, then x dot is going to be equal to 0. So if this is the case, then I pick x0 and u0 as an equilibrium. And it's not necessarily the case that a function f of xu will have exactly one equilibrium. Sometimes the equilibria for a function f could be all over the place. There could be many different points where it would be an equilibrium where there's no motion in terms of the state's derivative. So again, let's think about x dot equals f of xu, y equals g of xu. So this is the state space form of a system, and we'd like to be able to approximate this system. So how can we do that? Well, first of all, we're going to pick a point, x0, y0, and u0. And we're going to choose this point to linearize the system. And this is what we're going to call a nominal trajectory. Sometimes it's called an operating trajectory or an operating point. And so usually we pick this nominal trajectory or operating point to be an equilibrium point because the system is behaving at that point. It's not really moving around. But we'd like to be able to explore how does our system respond to a disturbance at this point, x0, y0, u0. So if we receive a disturbance, we'd like to know how is the system affected. Can we control the system back to its equilibrium point? So how are we going to do this? We're going to use the Taylor series expansion. So let's refresh what the Taylor series expansion means. So let's assume that we have our function y is equal to gx of t. And so x of t is a time-varying signal. I'm going to abbreviate it as just g of x because it makes it a little easier to write. So from the Taylor series expansion, we can get the function y by first evaluating g at x0. This again is our operating point. And if we want to know the value of y at other places, we've evaluated it once at x0. But now we add to that the derivative of x, or the derivative of g with respect to x, evaluate the derivative at x0, and then we multiply it by the difference x minus x0 divided by 1 factorial. So what we've done is said, I'm going to evaluate the function g only one time at x0. I'll evaluate its its derivative, first derivative at x0, and then I'll subtract the difference from where we are actually at x to where our operating point was, x0. And we do this also for the second derivative. So we take the second derivative of g with respect to x, and then we multiply it by the offset x minus x0 squared divided by 2 factorial, which is just 2. And in order to be correct, we have to do this for the third derivative, cubing the offset, and on and on and on to infinity. So if we could assume that x minus x0 is small, then we can actually approximate that y is about equal to g of x0, so that's the function's value at the operating point, plus the first derivative times the offset x minus x0. So it's not going to be exact, but it's going to be pretty close. So if we remember that g of x0 is just equal to y0, we can rewrite this approximation as y minus y0 is equal to the derivative of g with respect to x, evaluated at the operating point, times x minus x0. And we can actually further simplify this by writing it as delta y equals some slope m times delta x. So clearly, if we consider that y and x instead of delta y and delta x, clearly this function is linear. But it's not going to match the system exactly. It's only going to be valid if we're really close to our original operating point x0.